Yep, so not 100% sure what all Rob said because I was running around trying to figure out how to get a HDMI to USB adapter, or HDMI to USB-C. But Joe and I are going to be talking about hunting in memory. So basically being able to use PowerShell to look for injection in memory. And so kind of quick introduction. Jared Atkinson, I'm the Defensive Services Technical Director at Spectre Ops, which is a startup. And there's about 13 of us. And we do like hunting, we do red teaming, those types of services. I'm also a Microsoft Cloud and Data Center Management MVP. And so, are we good on this? Okay, yeah, and so I don't know a lot about cloud, and I don't know a lot about data centers, but that's what they decided to put PowerShell MVPs under at Microsoft, and so that's what I am. I also develop a project called Power Forensics, which is a PowerShell C#-based forensic tool set. And then let Joe.
So I'm Joe Desimone. So I work for a company called Endgame. Some of you probably heard of, maybe don't know exactly what we do, but we have an EDR product to help people secure their endpoints, hunt their endpoints. So I'm technically a malware researcher because that's originally my background. I came from a malware RE background, but since I've come to Endgame, I do development, I do a little bit of RE, I do a little bit of threat hunting, and also do this kind of hunting and memory stuff for Endgame, so it's fun. So just give an overview of what we're going to talk about today. First, just briefly talk about like why hunting in memory is actually important. We're going to then dig into some of the common attacker techniques. So really, if you want to be able to find stuff that's living in memory that's evading from you, then you kind of have to at least have some understanding of what the common techniques out there are. So we're going to just walk through some different malware samples and some common techniques and show you kind of what they're doing. And that'll help you when we go to how do we detect this, you can kind of keep that in the back of your mind. We'll talk about some existing tools and approaches that you can use for hunting in memory, and then we're going to be releasing a PowerShell tool today that can rapidly scale out and be able to find some of these techniques that malware is using to hide in memory. So the importance of memory hunting. It's not new. You hear like the buzz of fileless and stuff like that. Malware using in-memory techniques is not really new. It's been around for over a decade. If you think back, like Poison Ivy in the mid-2000s, a lot of APT groups using that, which had some fileless techniques, some injection techniques. But now it's really what's changed in the last few years. It's just become a lot more common, and those APT techniques have migrated to being commodity malware and stuff. It's really easy to just go on GitHub and grab some libraries already there for your malware and build it in and use those techniques. And specifically, it's designed to evade PSP products, but also you guys. You guys are hunting, you're trying to find stuff. The actors are using these techniques to hide from you guys, so you need to be aware of them and specifically use that through your thought process as you're doing hunting. But also, hunting in memory is great because if you do it correctly, it has a great signal-to-noise ratio. There's so many files and processes and DLLs loaded and all this stuff, and there's so much data, but really, when you're looking in memory, there are some legitimate things that are using in-memory techniques, but it's just a lot smaller. So if you do it correctly, it's easy button hunting. You can find the advanced stuff because they're being stealthy, and you can find them easily. So here are the attacker techniques we're going to go through. We're going to talk about classic memory shellcode injection. We'll touch on reflective DLL loading, which I'm sure a lot of people have heard of. Memory module, which is sort of newer, but it's kind of a twist on reflective DLL loading. Process and module hollowing we'll talk about, and PEB unlinking. And finally, we'll talk about this new technique that was within the last few weeks that come out known as Gargoyle, which is kind of cool. So classic injection. This is like Poison Ivy, bread and butter. You're going to, first you need to get a handle to a process. You're going to open process. You're going to allocate some memory in that process. So this is going to be unbacked code. Some people call it floating code. And then you're going to write your shellcode to that. And then eventually you're going to create a new thread of execution on that shellcode. So this is kind of like the original. This is the old school Poison Ivy approach. It's pretty, I would say it's not really stealthy, but it's just good to know as a base. So just some screenshots with Ali debug. You can see Poison Ivy, 40 at the top of the screen. That's something that you just can have in the back of your mind because it's read, write, execute. So if you ever see push 40 before a virtual alloc, it's going for read, write, execute. And then you can see at the bottom the write process memory that it's using with create remote thread and close handle. So that's kind of like the recipe for doing classic injection with Poison Ivy. I'm going to show a lot of screenshots of Process Hacker. I love Process Hacker. I use it a lot. So this is actually, if you look at the memory layout of the process been injected to, the cool thing about Poison Ivy is the way that it does this injection. It's not all in one chunk of memory. It actually kind of spaces it out, and it'll jump from region to region as that code is executing. So you're gonna, if you look at it with Process Hacker, you can see a whole bunch of different RWX sections, all consecutive, but all laid out there. Process Hacker is also cool because it'll show you call stacks for what's actually running in that process. If you try to do this with the Sysmon Process Explorer, they'll actually, really what you're trying to get to is those elements on the stack that the big arrow is pointing to that don't actually point back to code on disk. So it just says no unwind info, there's no file name. Process Explorer just thinks those are wrong and just deletes them, I think, from my own testing. But Process Hacker will actually show you. And that's really what you're looking for, because those are the addresses that are unbacked, the floating shellcode is actually executing to. Like, that's abnormal. You can see it's calling WinSock functions there. So yeah, that's Poison Ivy. We'll move on to reflective DLL injection. So this is kind of, this is a better approach, because when you think of Poison Ivy, you have to write your own shellcode. Like a lot of the adversaries out there, it's a pain in the butt, like to write your own custom assembly. All you really want to do is take your C, C++ application, build it, and you want that to load. Well, reflective DLL injection makes that a lot easier, and the original research by Stephen Feuer, he kind of published this, and it's really handy for like the attacker's perspective. That's why you see it all over the place, and it kind of makes for a dumb injector, because basically the target payload maps itself into memory. All you got to do is start a thread or redirect a thread to the entry point of that reflective DLL, and it kind of takes care of mapping itself. So it'll allocate memory, map sections, resolve the imports, fix up relocations. It kind of does everything. You don't really have to know about that, but there's just basically a header that you would include. And Meterpreter has been using this. I would say they were one of the first to like fully weaponize and make it a robust solution. So Meterpreter is using that under the hood. Even PowerShell Empire uses that under the hood when you want to do a migration from your initial PowerShell. You don't want to live in PowerShell.exe. You want to migrate to some service. Well, they're actually using reflective DLL injection in order to bootstrap .NET into that target process. So this is kind of what Meterpreter looks like with Process Hacker in memory. You can see there's a whole bunch of read, write, execute sections. That's really anomalous, I would say, to say the least. There's also some sections that they're close in size, because what happens is there's an initial allocation that happens, and then it reallocates itself with the correct page alignment. So that's why you can see there's like kind of multiple sections that are similar in size. But even more obvious, like if you actually dump out those sections of memory, open up with IDA, you'll see it literally has the reflective loader export. So it's, you could even look for that as a string, as like a super high confidence thing. But if you actually click on one of those memory sections, even the main header is there. So it's, it's really basic level, super easy to find. If it has the full MZ header still sitting there at the start of the section. Memory module is similar to reflective DLL injection. This is another one. So this is also, you can go to GitHub, download code to do it. And basically, it's similar to reflective DLL injection, but instead of including a library with your payload, the injector actually does the mapping for you. So you can just have your regular DLL. It doesn't have to know about being in memory. It doesn't have to care. But the actual, the main loader will take care of doing the same processes, resolving imports, fixing relocations, and that sort of thing. So it's kind of like just calling load library from the attacker's perspective, except instead of giving it a DLL path to something on disk, you just give it a chunk of memory. And usually that memory comes from something that they've either downloaded over the network or something they've just decrypted. So it can live on disk, encrypted, decrypt it, and then load it directly into memory. The original implementation avoided RWX, and most of the implementations I've seen avoid RWX, which is nice. So it's just going to, well, nice from the attacker's perspective. And so you're going to have like a read on the header, and we'll show some screenshots of that. And the original was a local process, but there's new implementations that will allow you to memory module into a remote process. So Net Traveler is one example of an APT implant that did a memory module style injection technique. So you can see they've if you look at the actual permissions, they're not super anomalous. Read write on the header, read execute for the code section, and read on the data and read write on the whatever the other data section is. But So if you're just looking for read, write, execute, you're not going to find something like Net Traveler. So that's something to be aware of. You can also look at the threads. Similar to Poison Ivy, even though they're using memory module, you're still going to see that there's that floating code unbacked memory there, which is trying to do HTTP requests. Winnti is another example that uses memory module. They got a little sloppy on their permissions, so you can see the header has read, write, execute. There's no reason for that from the functionality perspective, but you'll see in a second why. For Winnti, they were smart enough to actually wipe out the header. So I think what they did was, they had allocated it correctly, and then they just did, hey, I'm just going to read, write, execute this so I can write to it, and then they zeroed it out. So it's more difficult to find for Winnti, but it's still going to be unbacked code that's living there. Process hollowing, I'm sure a lot of people have talked about. Even Volatility's got some new research for doing more advanced process hollowing detection. But basically, this is the formula for doing process hollowing detection. Instead of injecting into an existing process, you're going to create a new one that's suspended, and then you do the allocation writing to, and then instead of creating a new thread, you're just hijacking that existing thread that starts up with that process. So you basically, the thread starts up, it's suspended. You can say set thread context, go over here, start executing with the payload that I loaded in there, and then resume the execution. And really where the hollow comes from is some typical implementations that'll free the memory of the original exe that loaded. There's actually no reason they have to do that. It's just done typically. And then kind of a more stealthy variant, I think Stuxnet was one of the first that I've seen that used the create section, map section. So instead of having to actually call write process memory, they can avoid that, and they can just map a shared view of a chunk of memory between their process and the remote process. They're writing to it locally like they normally would, but it's kind of mirrored in both places. So that's a good way to avoid detection from a PSP. And also, instead of calling set thread context, they can just write a jump or something at the starting point at the original module that'll jump to the new code instead of calling that suspicious API. DarkComet is kind of a good example of a piece of malware that uses process hollowing. And really what the key to seeing process hollowing, if you see a create process there with the creation flags of create suspended, you're probably going to be looking at process hollowing type technique. The interesting part is if you look at DarkComet after it's loaded up, you can see the base address of that main module, dark.exe, is at that hex address. But if you actually go look at the permissions of it and the type of memory that's allocated there, it's private commit, which should never happen. A module, either DLL exe, is always going to be mem image. So just the fact that that's pointing to a private section of memory is very anomalous. Module overwriting is we're starting to get into the more advanced territory. So up until now, all the examples that we've talked about really end up with unbacked code or floating code executing in memory. But some more advanced APTs can avoid this. So even if it's, they can actually live in mem image type memory. So this is something you should be aware of. But basically, I don't know if there's an official term for this. I'd refer to it as module overwriting. But basically, so Flame, what it would do is it would load shell32 into its target process. And the reason they chose shell32 is because it's huge. It's one of the biggest DLLs in System32. And the Flame implant itself was huge. So they didn't really have a whole lot of options. And Corrado, they would choose from random, a list of DLLs. Kaspersky actually had a great paper out on Corrado that you can read about. But basically, instead of creating a new suspended process, what they would do is they would have their target process, and they would map a new DLL that wasn't being used into that target process, and then they would overwrite that with their actual their implant in memory. So it's not floating, but it's living off on top of what was a legitimate shell32 Microsoft application or some other DLL. So Odinaff actually had a similar trick, but instead of overwriting DLL, they actually overwrote their own exe space, which was kind of different. And the way you would detect this is doing in-memory versus on-disk comparisons. So this is just a dump of the P headers of on-disk Odinaff versus in-memory Odinaff. And if you look at the the linker version, the address of the entry point, size of the code, it all differs between what's in memory versus what's on disk. And actually what it does is when it first starts up, when the Odinaff exe first starts up, it'll allocate a little chunk of shellcode that basically goes, and when that shellcode starts executing, it'll read back from the original file, decrypt that, and then overwrite the original code in memory and then jump to it. So it's a way for them to avoid being detected in signatures. It's not totally fileless, but it's still an in-memory technique. The true code that's executing is only living in memory. And the way you could find it is by looking at that delta between what's on disk versus what's in memory. I would say PEB Unlinking just deserves kind of a quick mention. It's not, you're almost getting into like rootkit type techniques, but it's still fairly common. So like Hacking Team use this in their RAT. Flame actually unlinks shell32. So if you're just looking for shell32 loaded into weird processes, you might miss this. So it's something to be aware of. It's something to look for. And basically the way you find it is, you can ask the higher level APIs that basically walk through the process environment block and give you the list of DLLs. And you say, hey, what's loading this process? And then you go ask the kernel with a different API and say, hey, what's actually loading this process? And you just, when you do a diff of the two, if there's something that the kernel's telling you is there that the higher level API is not telling you, then you've got some PEB unlinking going on. And then last, I'll talk about Gargoyle. So this is actually a cool technique. This was out pretty recently. So up until now, even with the mem image like module overwriting type stuff, you always have some +X section of memory that's running. And this is a security researcher, just proof of concept code. Basically, what he wanted to prove is that even if you're a PSP product or a hunter, you can't just rely on looking for +X memory, because what he actually proved is you can basically make the payload lie dormant in memory, and then he used like an exploitation style technique in order to mark it as executable on demand. So he's got like this asynchronous procedure called timer that basically triggers on whatever basis you want. You could set it for 10 seconds, 20 seconds, 20 minutes, hour, days, whatever you want. And basically, when that timer triggers, then it actually starts executing a ROP chain. And that ROP chain will basically set the permissions of your payload as executable, just for a brief point in time, start executing it, and then it sets up tail calls at the end of it and basically sets it back to read only and then goes back to sleep. So it's really cool. So you've got this piece of code that if you were just doing a quick sweep, just show me what's executable in memory, you might completely miss this technique. So it's something to be aware of. It's kind of new. I've never seen an actual implant use it yet. That doesn't mean it's not out there. If anyone knows of an actual implant that uses a similar technique, come talk to me, because I would love to look at it. But you definitely want to keep your eyes on stuff like this, because it's only a matter of time before you start seeing stuff like this, because it's a great evasion from security products. All right, so that's kind of like the run through of what the attacker techniques are. So how do you go and how do you find like these attacker techniques? Well, I think an important tenet is to be not signature based at all. It has to be based on the behavior. There's always going to be a new implant. There's always going to be new signatures, but there's only a limited set of the techniques they use. I like volatility and malfind for this reason, because it looks more on the behaviors of what it's doing. The only downside to doing like a full memory forensics is obviously like the scale. So it's good if you have like a suspicious workstation, you want to do a typical forensic process, then that'll work great. But really, like these types of questions, like, hey, what's running in memory across my network? Like that's something you want to be able to ask and have an answer back pretty quick, and be able, if you've got 50,000 endpoints, doing full memory forensics across those endpoints is very difficult. So that's the only drawback from like the full forensic approach. GRR and Recall, they're kind of similar, built on similar code bases. I think it's pretty cool. Like some of the scaling I've seen in GRR looks kind of cool. Like you can do, if you have a YAR rule, you can go search like in memory for certain techniques, and that would work for, let's say like the reflective loader. Like you could search for that string for any. You'll find some stuff with that, but it's not necessarily technique based. That's the only downfall. Invitero was something new to me. There was actually just presented at CanSec West not too long ago, and I think it's cloud focused from what I could tell. But looking through the code, he actually had some pretty cool detections that he had built in, like doing like call stack analysis and like ROP checks built into the tool. So I would say like keep your eye on that. That could be something that's interesting as it progresses and matures. But I don't know if that's still like more cloud focused or something that would be more applicable for workstations and stuff. But I think our approach, it's not going to replace full memory forensics, but you'll see that it's it's better for different ways, particularly for the scale and the fact that it doesn't use any type of like signatures and stuff. It's more based on the behavior. So kick it over to Jared, and he'll finish
Yeah, so if anybody's followed any of my work over the past few years, you know that I'm basically one of the biggest PowerShell fanboys. And so kind of a little background about that is I previously was in the Air Force, and Air Force, just like any big entity, has certification and accreditation procedures and a really long timeline. So if you want to introduce a new tool, you have to say, okay, here's the new tool. It has to go through months and months of certification and accreditation before you could actually use it. But I was told that, hey, if it's a script, scripts don't need to be certified and accredited, so you could just run scripts kind of willy-nilly. Well, PowerShell has access to the Windows API just like a C program would have, right? And so it's a little bit harder, I guess, or less direct to be able to call those APIs, but you could literally script anything in PowerShell. Anything that you would do in C, you could do in PowerShell on Windows. And so I decided to kind of go down that path, and everything that I do is a script now, although it's doing similar things to what those compiled binaries would be doing. So we're going to look at how we would detect that floating injection that Joe was discussing. One of the projects that this tool set or this script is built around is called PSReflect, and so this was written by Matt Graber, a former colleague of mine. You could check it out on GitHub. What he did is he allows you to use reflection, and he's kind of written a domain-specific language that allows you to call these Windows APIs from PowerShell without kind of knowing all the background that you would need to do it kind of on your own. There's a couple other methods or techniques that you could use from PowerShell to call Windows APIs. One is called platform invoke, or pinvoke if you're familiar with it. Platform invoke is not super clean. It actually does like just-in-time compilation of C# code to be able to access those APIs. And so there's compilation artifacts that are strewn about the file system. And so from kind of like a responder or forensic type perspective, or even a red teamer's perspective, platform invoke is probably not the best way to go. And so that's why reflection is really cool, because it all happens in memory. All right. So the script that we wrote is called Get-Injected thread, like I said, built on PSReflect. And so kind of the methodology that we use is we use Windows Tool Help API to get every thread on the system. Then we kind of iterate through those threads and then check, basically ask the thread, hey, what's your base address? What's the starting point in memory where the code for this thread lives? Then we query the memory page for that base address and check a couple things. One is we check to see if that base address memory page is committed, meaning it's allocated or it's being used. And then we check to see if the memory page type is not memory image, so meaning that there's a file backing that memory page. If a memory page or if a thread's base address is committed and not backed by a file, then that's what we consider a hit or something that we should look into. From that point, we go in and look at a few different pieces of information, and we might want to check like the memory page permissions. So is this page read, write, execute? Is it read, write? What are the permissions? We could look at unnecessary privileges or integrity levels. So like, does this thread have SEDebug privilege? Does it have like a high integrity level, meaning it's bypassed the UAC, the user access control prompt? You could also look for abnormal user tokens. Is this the process that this thread belongs to? Is it running under normal user, but has a system token associated with this specific thread? That might be something that's worth looking into. And so here's some of the things that we get in the output. So we get things like process information, process ID, name, the file path, and we query that in two different ways. So he talked about PEB Unlinking. But the process environment block is something that an attacker can change, and so you can't necessarily trust the information that you get back from the process environment block. And so what we can do is we can use different APIs to query the process environment block and the eProcess structure, which would allow us to compare to see if there's been any changes to the file path. We could also check the command line. We can then kind of look at the thread information, the thread ID, whether or not there's a unique token, user token for the thread, check the base priority. So has somebody made this thread more important than other threads? Does this thread have a unique token? Kind of already said that. And then the memory segment. So we could look at like the base address, the size, protections, state, type, and then I give you the first 100 bytes of the memory segment so that you kind of do a little manual analysis. And then kind of token information, integrity level, has this thread or token bypass the UAC? What privileges are enabled, like SEDebug, SE impersonate token, the SID or username of the token, login session start time, logon type, and then the authentication package used. So logon type might be interesting because you can check to see if it's been a network logon or like a local logon, for example. All right, so here's the first kind of demo that we're going to do. This is a really simplistic demo. Joe wrote a program called thread start, which is going to literally start an application and inject a thread that's not backed by a file on disk. And then we'll just show kind of generically detecting that. So, all right, just running Get-Injected thread once, showing that nothing came back. This is a clean system for now, kind of clearing that out. Now we're going to go over and double-click on this. We see that we've started a thread start.exe. It's malicious thread test. The thread ID is 2756. So now if we run Get-Injected thread again, we now see that we found a thread, which is thread ID 2756. We see it's threadstart.exe is the program that has been injected into. And then we're able to actually check the base address. So here you see 0xD0000, which if we translate that from hexadecimal to decimal, then we see it's 851968, which is what the base address is. So we see that this is detecting what we expect it to detect. This is just kind of our unit test, for lack of a better explanation. All right, so that's great. We detected our own thing that we wrote, and like it's super basic. But what about looking at some real malware that uses injection, right? So there's this Palo Alto Networks did a write-up on this Trojan they called the 9002 Trojan. It was delivered via a zip file from Google Drive, and then the zip file contained one file. So it was an executable that was masquerading as a PowerPoint presentation, right? And so it had the little PowerPoint icon, and so you would double-click on it. It would drop a PowerPoint file, open that file up, but also execute the executable. A couple files that it then drops are realnetwork.exe, main.dll, mpa-media.dll. MPA-media, realnetwork.exe is a real actual file. It's digitally signed by a legitimate company. But it's vulnerable to DLL sideloading. And so they drop a malicious mpa-media.dll file that then gets loaded up into realnetwork.exe, and then loads up main.dll, which is the malicious thread that's going to be created. All right, so let's check out what that looks like. All right, so you see here, running Get-Injected thread just to kind of show that nothing came back. And then you see there's a PowerPoint presentation over on the left side of the desktop. I'm going to double-click on it. It's really an executable. It just is masquerading. It opens up PowerPoint. You see that there's a file drop down below. Here's that PowerPoint presentation. And so, hey, it looks like it did exactly what we expected it to do. But if we go back, there's our new presentation. If we go back and we check the injected threads, we see that there's three injected threads, and realnetwork.exe is the victim process. So then we were able to see, for instance, the page is allocated execute read write, which is RWX. We also see that under the user folder, there is a directory that was created that's arbitrarily named. Oops. All right, and so if we look inside of that, we see realnetwork.exe, main.dll, MPA plugins, and that mpa-media.dll, which is that maliciously loaded DLL sideloaded DLL. One of the interesting things is that, bxqles directory is a hidden directory, so just kind of an extra thing that we wouldn't be able to necessarily see as easily without the injected thread. All right. So what are some responses that we could take to this type of situation? So let's say an attacker injects into LSAS or some service that's necessary for the computer to run, right? So you can't just kill LSAS because that'll blue screen your computer. How do you kind of get rid of this injected thread? Well, you can actually, because we know the thread ID and the process that it's in, we can actually go in and kill that individual thread. And so also wrote a PowerShell script that allows us to stop an individual thread, and that's built on Windows Terminate Thread API. You could also do process mini dump. So Matt Graber also wrote a script called out mini dump, which allows you to create a mini dump, which is like a crash report dump. And then you could use like WinBag or another debugger to kind of look through that crash dump to see what's going on. You could also do something like dump that thread. And so that's another concept that you would be able to do. So just dump that thread's memory address. So you could use like Process Hacker or PowerShell to do that. And so here's another kind of continuing on from where we started. We we're going to go ahead and kill the thread. So got process hacker on the side here. So we see there's 4 injected threads. We see real network.exe. We see thread 920, 1664, 1644, and 3244. Those are all malicious threads in real network.exe. So we go in, look at the threads here. There's a number of legitimate threads, but there's also the malicious ones. So go in. So we have thread 920. We could just say stop that thread, push enter, see it turns red and disappears. Kind of go through the whole thing and kill all the malicious threads. Let's see. This one was hard to do because one was 1644 and one was 1664. All right.
Dyslexia kicking in.
Yep. A little dyslexia going on. Yep. And then 3244. So this situation is a little bit contrived just because real network.exe was used specifically in this case to launch the malicious threads or malicious code. But in a situation where an attacker has injected into something that is actually a legitimate process that is critical to the system, you would want to be able to possibly get rid of the attacker from the system without crashing the system.